scholar. And there is another course instructor for this course named Chakravarti Jada. He is also in this call. So we both will be taking the live sessions alternatively. So our live sessions has been scheduled on Monday, Wednesday, and Friday. Monday 5 to 7 p.m., Wednesday 5 to 6 p.m., Friday 4 to 6 p.m. Kindly check with the schedule. I think the Friday schedule has now been updated. If you have seen a previous schedule, it might be from 6 to 8, but now actually the original schedule is from 4 to 6 on Friday. Right. So we will be recording the live sessions and we will give you the YouTube link for those live sessions after every session. Um, After every session you can but please make use of the live sessions because you can ask doubts and whatever difficulties you are facing we can get to know about yourself properly, like what is the status and how well you will be able to understand the concepts. Since everything is online, there is very minimum time to explain everything clearly. So within this period we will try to cover some portions. When you encounter different problems you might feel it difficult, so please try to attend maximum of the live sessions. It will be useful for you. If something happens, if you couldn't join the live session, then you can uh, use the YouTube sessions. And this live three live sessions has been classified in for three different purposes. Monday, most probably, we will cover all the contents what we saw during that week. For example, first week of Monday will cover the first week's content. We will explain all the concepts. If you, but you are expected to finish the videos before coming for the live session, so that when we revisit it, it will be clear to you. So wherever you have some doubts in the PPT, you can ask those things during Monday. And Wednesday will be the problem solving session, and Friday will be the doubt solving. If you have any doubts, we will clear those doubts, and also we will solve some problems. This is the agenda for all the live sessions. And if you have any doubts, please feel free to interrupt. We can discuss all those things in the live sessions. So, as this is the first live session, I would like to start off with the first week content. I hope everybody would have gone through at least what is the topics we have seen in the first week. Let me share my screen. If sometimes if the screen is not visible, my audio is getting interrupted, please let me know because I might have some other screen. I won't be able to see this Gmeet window. So please interrupt, unmute and interrupt me. Okay. Is my screen visible? I have presented.
No, man.
Okay. Mm, I'm trying to broadcast. Okay. Let me join again one minute, please. There is some issue while sharing the screen from my iPad. Let me try from my laptop. Okay. Right. Okay. Right. Um, I'll fix the problem from the iPad because it will be easy if I annotate it on live. Let's we can start seeing what the content is right now. So first week covers all the basics of the control engineering. Broadly in control engineering, what you would expect is how you can see a system, how you can represent a system in terms of a mathematical representation or a physical representation, and how you can work on those system to make the system give a response that you like. Or for example, if I want to turn on a fan and if I want it to run at 200 rpm, I can make the system run at 200 rpm with these tools what we are learning in this control engineering course. So the first week broadly covers all the basics, how a model of a system would look like, and what is a open loop system, what is a closed loop system, why we need feedbacks, and what are the types of systems, and what is the nature of any system, if you say. So most of the people would have covered some basics from signals and systems, right? If you have studied signals and systems before, this will be few basic weeks like for up till third week or fourth week, it will be easy for you because most of the applications are on Laplace transform and all the inverse Laplace transform. Whatever tools we learned on mathematic basics, either linear algebra or in more specifically in signals and system, because we might have used it to represent those signals, right? So it will be easy. Otherwise, you have to look up on those things. Little extra effort you have to make to understand those data. That's it. But we are here to help on those that on those topic. You can always ask us. So in module one introduction, I am assuming everybody would have gone through this. They have started with a single tank system example, where this single tank is considered to be a physical system where each and every system has one input and one output. This is a simple system, I would say. So there are many systems that has two input, two output, more than two inputs, more than two outputs. Those are called CISO. CISO means single input, single output. We don't tell TITO because it's like two input, two output, but it is not famous with that name. But MIMO is very famous. MIMO means multi input, multi output. So this two input, two output will also come under this MIMO. So whatever inputs that are more than one, we call it as MIMO, otherwise CISO. So there are some categories this CISO system holds, which is very easy, straightforward, and it's mostly it will be linear if no any external non-linearities happen there. And this MIMO system is little complex to handle compared to this CISO systems. Right. This tank system we are considering single tank because it has one input and one output. Very simple, straightforward system. Right. Now the actual physical thing happening here is we want to control the level of the system. This is the control objective. So we have few keywords in control systems called as objectives, control objectives, inputs, outputs, feedbacks, and control signals or control what to say control input, actuations, sensations or sensors. So these are all some technical terms we used to use while taking these tools in a control systems. Here we say I want to maintain the level of the water in the tank. This is my control objective. This is what I need. So for that, what I can manipulate. That is the overall story behind this. So if what will then for to manipulate what to see what I can manipulate, I have to know what is affecting the system, right? So here the inflow is the major parameter that affects the level of the system. If the inflow keeps coming inside, the level will get increased. So I cannot control over that. So somebody should be there physically present to monitor the inflow so that the level would not rise over the particular benchmark or some particular level, I say. So who will do that? Instead of doing an external person, some manpower to do this, we are automating this by introducing a control signal inside it so that this control signal will monitor the inflow rate and the outflow rate so that it will maintain the level. This is what we are going to study. This one tool that we are replacing this manpower, right? This keeps on varying over from we go from week 1 to week 12. So this control actions can be done in many ways. There are many controllers, PID controllers, on-off controllers, bang controllers, so MPC controllers. So there are many different controllers for what actions, which controllers we should need and how to design those controllers. This is the way we are going to see go from basic controllers to advanced controllers from week 1 to week 12. So then for the basics to understand the mod system, we are going for system modeling. How can we represent a system physically or mathematically so that it is globally understandable? For example, I may have different cooker. My friend might have different cooker, right? So if you want to globally represent this in terms of a single thing, we need some mathematical representation. So that's what we are doing here. Same thing what we did. So coming to the feedback, this is the important parameters in the control systems where If you want to replace those manpower who is monitoring the flow and all, we need someone who's similar to that, right? That part is being done using this feedback. This what this feedback would do is, this feedback instead of that person will monitor the output and combine that knowledge and give it back to the system via input. This is the um, job of this feedback. So this feedback will have, sorry, will be there in the system, below the system, where it will get the output, do some work on it so that we will get the desired output response again in the second iterations. So this output will be fed back through the input by making some modification, so the system will behave according to our wish. That this is the idea behind this feedback. This feedback can be of two types. One is positive feedback, another one is negative feedback. Usually, negative is a bad thing, right? But in control system, negative feedback is a savior. Positive feedback is the bad thing here. Positive feedbacks mostly be used in terms of oscillators and all. If you want to generate a constant oscillations, we will go with positive feedbacks. But in general, we would want to get a stable or static outcome, right? For example, 200 rpm, as I said before. I don't want 100, 200, 100, 200 rpm changing from one place point to another, right? So oscillatory responses we don't want. We want a stable or finite or static responses. Those are all good terms in terms of control actions. So for this, we might need to use negative feedback only. Here in control system, negative feedback is the savior. And feedback, we have seen feedback will work in the uh, outside loop. For example, if this is a system I am representing here, so if this is a system, there are, in control systems there are systems like open loop and closed loop that we are going to see later. So open loop in the sense there will not be anyone to monitor. The input will be given and the output will come in spite of all the conditions whatever we need. We cannot control anything about the system. Whatever input you are giving, based on the input only you can control. For example, if you give low voltage, it will, the fan will rotate at low speed, but it cannot be guaranteed that it can run at 100 rpm or whatever rpm you need. If you give low voltage, it will run at low speed. If you give high voltage, it will run at high speed. This is the open loop system. But when it comes for a closed loop system, this feedback comes into the picture, where this feedback lies here down the system. If you want to represent as a block diagram, it will take output from here and do some operation and fed it back through the input again, so that we can get the desired response. Similarly, feedback, there are systems called feed forward system, which will be on the same loop, where we have this input to output and in between process, right? So the feed forward will be there, will make this work here itself. Don't, it won't lie here. If it lies here and fed back the output as input, then it is feedback. But if it takes the input, do some operation and give it to the process without going to the output, then it is feed forward. So these are two different things we can see here. As I said before, negative feedback is popular. Compared to feed forward, feedback is popular. We most probably we will use feedback control systems with negative feedback. But these are all there for you to know what is the difference between forward and back and positive and negative. We will see few details about it also. Right. This K is the gain. So how to choose this gain? These are all introduction and motivation for this. So how we are choosing this gain, how what controllers we are using or what methods we are using, that's what we are going to see later. For that, we just it was given as a motivation. That's it. Right. As I said, open loop. You give the speed, you fix the rating or voltage level what you're going to do. For example, 1 means low voltage, 5 means high voltage. The fan speed will change accordingly. There will not be any regulation there. You cannot fix the system to work in a particular way. For that input, more or less it will work. That's it. For example, it will work in a range. For 52, for 1 to 2 voltage, it might run in 50 to 60 rpm. You cannot fix I should get 55 rpm. That is not possible with the open loop control. That's it. So these are all the conclusions I want to say. These are very essential components of the control systems, where it has controllers, actuators, sensors, and plant. Where actuators are the actuator generally lies in the output side. For example, if I take a motor, I am giving some supply, voltage supply, and it is this motor. For example, if we use motors at our home, right? So it will take water from the borewell and supply it to the overhead tank. So this mechanical thing it is performing, this is the output. So this mechanical output, what you are getting, the work has been done here, right? That work is considered to be the actuation. That process of making the work done is the actuation, and whatever system it is doing, that is known to be actuator. That's it. Sensor, in the sense, sensor won't make any work done, but it will tell the properties or the nature or the value of any system. For example, if I keep a thermometer over that motor, your motor that has been used in your home, so that thermometer will tell the temperature only. It won't let the water go from borewell to overhead tank, right? That thermometer is a sensor here that will represent the nature of the system or value of the system. So you can make a informed decisions. For example, if the temperature goes beyond 40 degrees Celsius, I have to turn off the motor, otherwise the winding will burn. So this kind of informed decisions you can take using the sensors. So sensors will always lie in the feedback, this loop, feedback loop, down loop, so that you can make informed decisions about the output. Right. So, for example, some sensors you are keeping to monitor the water flow. If the water flow is too much, you can control the water flow. That will be taken as a feedback and give it back to the motor as a voltage changing parameters, right? So that you can reduce the voltage or increase the voltage accordingly. So please get yourself familiar with these terms. These are going to be to come until the end of this topic. So how many of you are new to this control related things? For example, if you have done something related to electrical, you would have come across the signals and systems and all. So you can just raise your hand. How many of you is very you think this is very new to you? I can change my mode of representation accordingly. That's why I'm asking. Knows this, or anybody is very new to this concepts? Is everyone
Not
with me?
completely.
Should I call your names?
Ma'am, we have heard about this topic, ma'am,
I, not audible.
but not completely new, but we have
Vinayak,
heard
you're
from
trying to speak. I think you're not audible to me. You can type in the chat if you want. Okay, this is supposed to be a interactive session. So if you people can interact more, it will be good. Otherwise, this is like a recorded YouTube live session only. Okay, not new to this topics. Okay, thanks. Right, so I can reduce my explanation about the concepts, and I can go more into the details of the things, right? So, right, thanks for. Okay, the next lecture covers we are jumping into the nature of the systems. Like there are different types of the systems. It has been grouped into different pairs. For example, static versus dynamics, linear versus non-linear, time variant versus time invariant, kind of many pairs we have, and everything is a representation of the nature of the system. So the lecture two covers the particular topic on static versus dynamic. So what are static systems? What are dynamic systems that we are going to see here? So these are some examples. Okay. Generally, a static system. Oh, screen is not visible. Thanks. One moment. Okay. Wait, it's still not working. Okay. We were saying about these different types of systems, right? Static system is a system whose output at any given time depends only on the input. For example, the output of the system depends only on the input, not any external factors or any other input that has been in the past. For example, I am giving 2 volt now. I'm getting 100 RPM in my fan, and if I increase to 3 volt, I will get sim like corresponding RPM, right? Some 300 RPM, for example. But it won't hold the memory of the previous inputs. That's what the static system is. Just static system behave straightforward as it is. Whatever input you are giving at that moment, it will behave like that. For example, it will give output based on the current input. That's it. No memory about the past inputs or any reference or any states. In on the other hand, the dynamic system, static systems are can also be called as memory-less system since it doesn't hold any memory. And on the other hand, we have dynamic system which depends on the previous inputs or past inputs, and we call it as memory system or system though it has which has memories. Okay, it depends on present and past. Both present, it can depend on both present and past signals. That's what the dynamic system is. For example, a series RLC circuit, they're saying RLC in the sense the L and C are the energy storing elements in this system. So physically, this even though the input changes with respect to time, it holds some of the energy that has been fed because of the previous inputs. So that it takes time to depreciate, right? It takes time to exponentially decrease it. So those has the memories of the previous inputs. So that's why we are calling those as a dynamic systems. So that's it. Then comes the next lecture, which is on linear versus non-linear. Okay. Linear systems, the next classification when compared, previously we saw how the system being called based on the how it behaves to the present input and present and past inputs. So those are called static and dynamics. Now the another representation of a system is linear versus non-linear, and you should keep that in mind, that a static system can be linear or non-linear, or a dynamic system can be linear or non-linear. So whatever types we are seeing, we are going to see in this lecture, it's not exclusive. It can be a mix and match of all those types. Just we are taking two pairs that are polar opposite to each other and we are comparing for now. That's it. So it can be of any combinations with respect to anything a system can be. So that we are going to see collectively when solving a problem. So when it comes to linearity, why this linearity is very important is that when we design a controller, we should know whether the system behaves linearly or non-linearly. For example, there are many controllers. With respect to systems, controllers also have classifications like linear controllers and non-linear controllers. Linear controllers can control a nonlinear system up to some extent only. We cannot guarantee the linear controllers will work for all the states of the nonlinear system. So there comes the discrepancy, right? So before that itself, you should know whether the system is linear or nonlinear. That's why we are taking this as a classification into a system. Linear system behaves a linear property. What are those linear property? It has two different characteristics. One is a homogeneity, another one is a superposition principle, where for example it was given here. So it should be the function. For example, if we have two different variables f of x comma y, then it should satisfies the linearity. A of x, x plus y, function of x plus y should be equal to function of x plus function of y. So collectively, if you sum those inputs, and individually if you sum those input, if you sorry, if you take one input and find the function of this input, collectively if you take and take, I think this is not clear. Wait, let me explain. It's something easy. Okay, here. So if there are two systems, right? System one and system two we are taking. We are giving two different inputs to both the systems. So respectively, we are getting some output. So for first system, when I'm giving an input as x1, we are getting y1, and x2 for the second system, we are getting y2. So now we are summing up these two outputs. That is y1 plus y2. So this is, we will keep this at one point at one side. Now we are summing this input as a different scenario. In a different scenario, consider this as a separate scenario. Okay, above this is a separate scenario, below this is a separate scenario. Now we are summing the input and then giving back to the system. We are getting some summed output. So these two should be equal for any linear system. That's what, whatever operation you're doing, there should be the input collectively you are getting, and if you do the operation, you are getting an output, and individually if you do, both should be the same thing. That's how the linear system works. So if this is not equal to y1 plus y2, then the system is non-linear. That's it. Similarly, if this is superposition, homogeneity, we have scalar multiplication. Every time, even if we see vector algebra and all, we have both properties like additivity and homogeneity. Additivity is the superposition here. So we will see x1 plus x2 is equal to y1 plus y2. Is that same or not? Other than is a into x, scalar multiplication we will see. That's the same thing we are doing here. First, we are giving a input to a system, we are getting one output and multiplying some scalar into it, and we are having one output. It's a different scenario. And in the second scenario, we are multiplying that scalar with the input and giving back to the system. That system is supposed to give the same output as previous scenario. In that, if the system is linear, otherwise the system is non-linear. Right. So there are some examples for non-linear system. So generally, linear system, the output of the system varies linearly with input, just like this. There's linear variations. Y equal to mx, for example. Non-linear relations between input and output. It has some curves or squares or sign trigonometrical or some exponential behaviors. For example, you should be careful. They If in case of exponential behavior, it should be in in terms of input only, e power x of t, then it is nonlinear. E power t into x of t is not nonlinear just because it has some exponential. So you should be very careful where the nonlinearity lies whenever you are solving a system, right? Then we are moving towards the next classifications: time varying or time invariant, and causal and non-causal. And time, from the name itself, we will know, right? Time varying means the input and the output varies with respect to time. Or the system, if it depends on the t variable, where t represents the time here, small t, then it is a time varying system. Otherwise, if the system's characteristics remains the same for all the time you are considering, then it is a time invariant system. That's it. So then causal versus non-causal. This is also an important classification, because for the causal system, many of the design criteria, whatever we are designing controllers, if we want to design, the design criteria can be minimized when the system is a causal system. You don't have to worry about it if the system is causal. For example, it is straightforward as linear. If the system is linear, similarly, if it is causal, it will be easy to handle. We don't have to see multiple checks, or we don't have to worry if about the negative signals and all. So most of the natural system is on causal systems. That's why. So causal depends, the output depends only on the inputs, present or past inputs, not on the future inputs. You might get confused this with the static versus dynamic, right? So for static system, it is only depending on the present input. If it depends on the present, it is static. If it depends on the present and the past, then it is causal system. So causal system will be dynamic or static.
Static.
What is your guess? Can causal systems be dynamic or static? You know static dynamic, right? Static depends only on
Static in nature.
present,
Non-static.
dynamic
Oh,
depends on present and past.
yeah.
Then if a
Dynamic
system is causal, output depends only on past or present, then what can I say about it, whether it is static or dynamic?
causal systems are static and non-causal
Static,
systems are
okay.
dynamic.
So, okay, I will make this statement. Causal systems are always static. If you agree this, give a thumbs up. Or if you don't agree, give a thumbs down. But either way, you have to react. Okay, right. Thanks for the response. So here in causal system, you can see output is only dependent on inputs already received. It's either past or present. It doesn't say past and present, right? So it can be only present. If the causal system depends on only present, then it is a static system, because static systems output depends on present inputs. If the causal system depends on past, then it becomes a dynamic system because it has memories, right? So causal systems are all not always static, but causal system can be static. That's it. So the statement I made, that is false. So causal systems can be static or dynamic based on what input it is depending on, right? The causality, the main point here, the causality varies with respect to the future. There is no future in dynamic or static, right? We haven't mentioned anything about future in while comparing the dynamic or static. If it depends on future input, if it predicts or if it waits for any future inputs and then take a decision, then it is a non-causal system. Most of the things in real time is a causal, because we don't believe on in the futuristic behavior of any systems until it is any predictive system. For example, a weather predicting behavior, or any ARIMA, like auto regression integrated systems. So those kind of systems comes under non-causal. But in general, practical systems, whatever we are taking, fan, light, whatever we are taking. It doesn't wait for tomorrow's input, right? Whether I'm switching on that switch tomorrow, it doesn't wait for it. So those are all causal systems, right? A non-causal will be will come only when future comes, future input comes. Just keep that in mind. Please don't get confused with the causal and static, right? Those are two different classifications. Okay. Okay, these are some examples they have given. Okay, this lecture covers only the examples for understanding whatever we have seen so far. The first example is a DC motor. So, what do you know Faraday's law and all what basics we have studied so far? Whatever it converts electrical to mechanical, we call it as motor. Mechanical to electrical, we call it as generator, right? So, this is a motor where it gets an electrical input and gives out a mechanical output. And these are some important details they have given. What are the input can be armature voltage and output is the angular velocity or angular position, both can be expected. And whatever you are interested in, you can measure that, or whatever sensors you have, you can measure those things. If I have a odometer or any wheel encoder, I would go with the angular velocity, or otherwise I will go with the angular position if I'm very interested in that. And this are the governing equation. The important point here is we will study some of these things, how to write a mechanical equation or a mathematical model of any system in upcoming lectures. So you should look this carefully. So it needs some basic physical or physics based details, formulas and all. Mm, KVL, KCL, some general very basics, Ohm's law. So those are the things you have to learn to understand or write this mechanical equations, mathematical equations of those systems. So here they have represent this equation. This it's a combination of, for example, VA is a armature voltage, V equal to IR. That is a Ohm's law, right? V voltage is equal to current into resistance. So that's what we have written here. When we instead of this diagram easy to understand, we if we give us a um, what do we call schematic diagram with the resistance and inductors, whatever um, electrical component lies there, it will be easy for us to write this equation. Otherwise, it's little difficult. So from this, I would say it has one resistor and one inductor. There is no capacitor. So they have written whatever current that is being passed through the resistance, that is I into, sorry, whatever voltage that lies between the resistance, that is I into R, IA into RA, because armature resistance into armature current, and the voltage across a inductor would be L di by dt. So it's a amount of the inductance with respect to the differentiation of its current, because it's a energy storing element, right? So it's kind of differentiating. Integration can be mimicked as a addition, right? So if we add minute details and secure that into a variable, then it becomes an integration. The vice versa is the differentiation of this. And we have some back EMF that is being represented using this KB into omega, where omega is the angular velocity. So these are some physical representation, or the parameters that has been used to represent this system. Similarly, a gear. So if we go this in detail without knowing the modeling, it would be difficult. But we will revisit this example when we learn the modeling, right? So some mechanical examples they have given, electrical examples, and RLC circuits. So this is what I told. So if we represent in terms of schematics, so this is a voltage coming in the same loop. So everywhere the voltage will be different or same. Voltage will be different or same in a series circuit. We might have learned this, no? For a parallel circuit, voltage is dash. For series circuit, voltage is dash. It will be different, yeah. For a series
So,
circuit, the voltage will
in-
be different. For a parallel circuit, the voltage will be same. For example, the voltage across resistance, inductance, and capacitors here will be same, but the voltage across these elements will be different as they are in a series circuit, because this consumes more, and again when it goes here, it will degrade. Again, it goes here. It might change based on the parameters or the value of those elements. Okay. So for solving this, you need to know basics of mesh analysis and node analysis. I think it will come in basics of electric circuits course. Otherwise, you can find it in internet. It is very easy how to represent a system, electrical system. That's it. So if I want to teach this, the voltage starts here, right? It starts here and goes here. So every time when we represent a voltage, if I want to write it in terms of KVL, so I will give some symbols so that I won't make mistake while writing here. So if I start with plus minus here, always top plus, bottom minus. So I'm explaining this for those who doesn't come from an electrical background. So always top plus, bottom minus, and whatever element it is there after this voltage source, start with plus. Don't get confused, because plus deviates, or plus cannot, like kind of magnet, when we compare magnet, this might, we might think this, right? I will at least think about it. So I get confused when learning this. So always start with plus, and start other symbols alternatively. That's it. If it this is plus, the other end of the resistor would be minus. Similarly, it starts with plus and minus. Only here same signs. Right. After that, you in here also same signs, minus minus, whatever element it is ending with. Right. Now start writing this. Keep this in the left hand side. Otherwise, write in the same equations. If I write, I will start with minus Vs plus R into I, whatever current flowing here. Otherwise, minus Vs plus Vr plus VL plus Vc equal to 0. This is what the actual equation is. I will repeat again. Minus Vs plus Vr plus VL plus Vc equal to 0. This is the equation, actual equation. So the only thing that is minus here, that is the Vs, right? So I'm taking Vs to the left hand side and keeping everything else on the right hand side itself. Instead of 0, I'm keeping Vr, VL, Vc, both all are positive on the right hand side, and taking the minus Vs to the left hand side. Now it becomes Vs equal to Vr plus VL plus Vc. That's it. Now the equation has been formed. Instead of writing VLVC, that doesn't give any extra information, I'm going to write it in terms of the element that is being present there. So if the voltage across the resistance, we always write it in terms of V equal to IR, right? I into R, linear relationship. And the voltage across the inductor, since it is an energy storing element, we would write this in terms of L into di by dt. Whatever current you are giving to it, they are taking the differentiation of it and multiplying it with the inductance. Then comes the C. C would be written in terms of integration of C into integral I dt. That's how we represent the voltage across a capacitor. But in general, we will stick to one format. So we see we being represented like this only, because it will be difficult to put integrator and all. So we are keeping it simple like this. So if you want to represent everything in terms of current, then you will go with that. Then VL will be VL only. The in voltage across inductance will be VL only. Right. I hope I am not confusing you. If you get confused, please let me know. Because I thought I can use my iPad to represent all this. Unfortunately, the screen broadcast is not working there. You're getting confused.
no, ma'am, it's okay.
Should I be more clear? Any other explanation you need from my side?
No, it's fine.
Clear. Okay. Thanks. Okay. So this is how we represent a circuit. Similarly, for parallel circuits, it's little different. Instead of mesh, we will go with node analysis for that. We can solve some problems and see those things in details. Instead of I'm translating everything doesn't work, I think. Okay, then comes the mechanical systems. So far, we have seen the electrical system. Now, there are in mechanical systems. There are two types of systems. One is actual mechanical system. Other one is a rotational system, translational system, and rotational system. Translation system gives all its mechanical energy in terms of linear directions, either x y x x minus x x or minus y y. That's how it gives. Rotational systems gives out of energy in terms of rotations. For example, motors. Linear systems, I can say, um, what can what can be given as an example for a linear system? I couldn't think of anything. Injection, maybe. Yeah, it won't rotate, right? The syringe will just push the whatever content it is inside through the needle, right? Injection may be an example for a translational system. Okay, so here we have different elements here. For example, in terms of translation system, you will have mass, inertia, sorry, mass, what is the spring constant, and another one thing I'm missing. I don't remember what the B is. One is spring constant, mass, damping. Damper will be there in
Ma'am,
translation
damping
system. In
coefficient.
rotational system,
Damping
same
coefficient.
mass will come. Instead of that, you will have inertia, and spring might be there based on the nature of the system. So it varies, right? So you should know how to write the explanation equation for those. How when it comes to a mechanical system, instead of RLC, you would have MBK, like mass, spring, damper. J, theta, angular position, angular velocity instead of normal velocity. So here we will track the position, velocity, and acceleration. In terms of rotational system, it will be angular position, angular velocity, angular acceleration. That is the difference, nothing much. For that, you have to introduce the parameters, whatever you are using in your system. That's it. This is another example. It's just a very famous example. Control system overall course will have very few examples. You can count it in your fingers. 4 5 examples you will have that we will use again and again. For example, pendulum, simple pendulum, rotational pendulum, and inverted pendulum, and this mechanical devices, mass spring, damper systems, aircrafts example, missiles examples. So these are some practical example we can get to connect. Some practical examples are very complex to represent for this basic course, right? So we will restrict ourselves for some famous example. If you get to know this example, cruise control, for example, if you get to know this example, you would feel connected to the course. Like you will know the course much more better than some other people you don't know, who don't know this. So that one such example is the simple pendulum example, where we can introduce the systems to our new students. They can learn easily with these systems. So these are some simple systems where you can understand the physical behavior of the system and you can represent it mathematically. Both ways you can do this. Right. Here we are talking about the torque and gravity, right? And for example, the lossless system, lossless is a simple form of the simple pendulum. That's it. Sorry, simple form of the pendulum. The equation represents theta double dot. Whenever there is a theta, we call it as angular position. If there is one dot, it's one differentiation, that is angular velocity. Double dot, double differentiation, angular acceleration. So it comes like that. Position being differentiated gives velocity, velocity being differentiated gives angular acceleration. On the other way, acceleration integrated will give velocity, velocity integrated will give position, right? This is same for both linear and angular. Now it was being represented using theta double dot, means angular acceleration. So whatever acceleration, at what acceleration this pendulum is being run from one point to another point, it's being hung from one point to another point. That angular acceleration being represented using theta double dot plus g by L. This is a mathematical explanation where g represents the gravity and L represents the length of the system. So, and sine theta. Sine theta is theta here is the angular position of the pendulum. So if the this is being created based on the relation between the length and the gravity, gravitational constants. Gravity comes into the picture because if there is no gravity, there will not be any motion, right? So, based on the gravity and the length, particularly of length of this pendulum, what is the angular position? That relation it is being given using this equations and its angular accelerations, right? With friction, so if there is some bush or uh, some element to hold the pendulum or some element is kept besides the pendulum, then friction comes into the action. It will give some other external force than the lossless, like without friction system. So that being represented using this B by ml square relation, that second term relation between them. So there comes the angular velocity also. Velocity also being considered here. Okay. So these are some different cases. For those who have done control engineering before, you would be very familiar with this undamped, overdamped cases where I can explain this concept using the door. For example, if you have a AC room and you have a door with that automatic stopper or automatic closer, right? So if you leave the door at any position, it will come to the closing position. That kind of door we use for any AC room to not let the cool go outside. So that particular element that gets the door to the closing position, it's called the damper. So based on the value of the damping we are fixing on the door, that's how fast the door will come to the closing position. So if the damping value is very small, it will take much time to close. If the damping value is very large, it will just close suddenly when you left the door. It will make a noise, right? So we will adjust the damping based on the value or how fast the door should close. It should not make any noise or it should not too slow to close so that the cool will go out, right? So it should be at the particular value. So that particular mean value we are choosing can be translated as a critically damped system. So critically damped system will behave ideally. You cannot expect any system to behave like that, but still it is there in the subject because it should also be considered, right? It should also be in the, even though if it is not, you cannot expect that practically there are some here and there would be there in any practical system. Mathematically it is easy to represent. It is so otherwise I can say we will be able to represent those systems. So that is there in the topic. So that system, that ideal system is a critically damped. Overdamped is in the case I say that it will come fast and it will slam the door. It's kind of systems. Underdamped is takes very time, very less time to close. These are different classifications. Undamped is that there is no damping. You have to close your door by your hand. That's it. So these are four different classification in any control systems: undamped, underdamped, critically damped, and overdamped systems. So based on the value you are choosing, the parameters we used to call it as zeta. So it comes when you learn the second order system later in week 3 or week 2. So based on the zeta value, the behavior of the system will change. That's how the name will also change. Whether you have to call it as undamped, underdamped, overdamped, or critically damped. Kind of four different damping we would expect. Another example is a predator prey model. I don't know. This is maybe we can say, for example, if I consider a swimming pool, for example, pond, okay, there will not be any fish in the swimming pool, right? If I consider a pond, I can say this predator prey model can be mimicked as a big fish and small fish. So if there is one big fish and one small fish, and I'm assuming that big fish can eat small fish. So if there is only one, both of that, anyway, big fish is going to eat the small fish. That's it. End of the story. But this predator prey model comes when you want to study the dynamics of any systems. If there are two or more agents in any systems, these are not like a physical fixed system where one input comes, one output comes. That these are not like this is little complex systems where multiple agents are there, and you want to study the dynamics of those agents or any states. Multiple states are there. You want to study those dynamics of those states. For example, if I have four big fish and have 10 small fish, and I have put these 4 and 14 overall fishes into a pond on day 1, and if I'm coming back on day 5 to see how many big fish and how many small fishes are left. So if here the dynamics change based on how fast the big fish eat the small fish, right? How well he's able to maintain his hunger. If it is hungry, it will eat, otherwise it won't. But if there are two big fish and if there are 100 small fish, I would definitely say after 5 days there will be some small fish left, right? There might have some small fishes. But if there are two small fish but four big fish, then what do you say? You cannot say that big fish will be there because there will not be any food. Big fish also might die, right? So this kind of dynamics we will study using this predator prey model. So whatever, if you have multi agents and if you have multiple states, if you want to study the dynamics, that model has been called as predator prey models because it mostly in biological systems we use these terms. Algae, those kind of relationship if we want to study, we will go with this predator prey model, and we have definite physical representation for this, that is this x dx by dt is x dot. So x is any state, not position here as we see in mechanical systems. Here x is any state we want to study, maybe the life of the big fish or maybe the life of the small fish, that is being called as x here. So by by dx by dt is we are studying the history of the x, how well the trajectories of the x being changed over the time. That's what being called as dx by dt. It's a change of states. So the x yesterday how it was, now how it was, uh, tomorrow how it will be. Those kind of studies we are getting using this dx by dt. That's why we are representing it in terms of differentiation. Okay, these are some gist of the week one. I hope you would have attempted the practice assignment and graded assignment. And some people have asked question in that group, and I don't understand basically. I didn't answer, and some of you have answered it. But if you still have any doubt, please ask me now. I just want to understand what happened there.
Ma'am, in the last two questions given in the
If
graded
you have
assignment,
any, are you facing any difficulties in practice assignment or week assignment? If you are facing, let me know. Linear system problem. Which problem you are facing? I will see. I'm opening that your portal. PAQ4. Practice assignment question 4. It's loading. Which of the following is the linear system? That question, right? That has been put it in the discussion group. Okay. These are all the few examples it has been given. First one is 3t plus 7. Okay, the first one is a non-linear system because it's not y equal to mx, it is y equal to mx plus c. There is a additive constant term there, right? So if you do the f of x plus y equal to fx plus fy, it won't satisfy. First one is a non-linear system. The second one is also a non-linear system because it has t square. Third one is it has exponential, so not linear. Fourth one, it has cos. Okay. Mm, sorry, trigonometric terms. So it is also a nonlinear system. So none of the above is the answer for this. But what was the answer for it? A was given as an answer. Oh? Okay, then it is a mistake. Yeah, it should be either it should be 3T, otherwise none of the above is the answer. No, no answer should be the same. Right. Since it is a practice assignment, it is not a problem, but we will be careful when it goes for graded or like quiz problems. No, thank you for pointing it out. Okay, any other doubts you have? If you have, we can discuss further. I'll be available till 7. If you have any doubt in the lectures, if you don't understand any concepts, you can let me know. Otherwise, we can wind up the session. When is your quiz, Mon?
Ma'am, 26th October.
Last two questions of double week one graded assignment. We are asked to use simulations to find answers. Okay, are we expected to mark a MATLAB simulation file? Simulation code be provided. Uh, Let me see. Week one. Okay, week one. Last two questions. Sir. Consider the equations of pendulum which of the following some under damped system. Why do you need simulation here? Week one graded assignment, right? Okay. Okay, right, right. You can use simulations to find the answer. That's it. You don't have to submit or anything.
So these questions don't have
Submission is
grading, is
not
it?
needed. If you want to know or if you want to visualize, you can use the simulation to know that. Since they have asked about the underdamped and all, I will solve some problems there tomorrow, like Wednesday, on damping. Because I thought in the lectures notes there was no information about the damping, right? It is coming later slides, but I will let you know about how to find damping and all. We can solve some problems on Wednesday.
Yes, ma'am.
Meanwhile,
The
try
simple
solving the
pendulum
graded
damping was
assignment. If you
covered.
have any doubts, we can discuss on Wednesday. It's on 5th March is the deadline, right? Sorry, 5th October is the deadline, right? We can we'll have session before that. We can discuss those doubts. I cannot help you, give you the solution for that until you submit, but we can discuss if you have any doubts. I can help you to get into the answer. And there will not be any mark for any quizzes or any instance anything, and we won't be giving any solutions to the assignments also. So please solve some of the problems in the assignment by yourself, because it will be helpful when you prepare for midterms or sorry quizzes or insims, because the professor's instruction is like that. Professor doesn't want to spoil you with the solutions so that you will be lethargic at first and you will just study it one day before night. So please try solving the problems, but we will help throughout when you have any doubts in that thing. 1 minute. Okay, reference books you're asking. Anything it was given in the website, so I can give some other thing, some other books other than that. Ogata, yeah, it is there in the website. You can follow. These are all the books we all also generally follow. Mostly, you can use model control engineering by Ogata and feedback control for dynamic systems using by Franklin, Gene Franklin. So these are some basic books. We will also um, teach topics from these books only. We will follow these books. You can use the same reference books. Other than that, for basic control system, there is a book by Norman, but it will be rigorous only. It will not be as easy as Ogata because Ogata you have some MATLAB representation and all. It will be easy, but for those who want to study further, you can consider Norman, NORMEL, same control engineering or something like that. Control system, something it will call. It will be rigorous, little bit rigorous. Proof wise, it will be very rich. Right. If you don't have any doubts, we can wind up the session. Wednesday, we will solve some problems. Thank you. Thank you for joining.
Thank you.
Thank you, ma'am.
If you have any doubt, you can stay back and ask. I will be here till sometime. Thank you so much. Jada, you're there?